Hi everyone, so we are back in our signal and system course. So this is going to be day 4 and we are talking about the basics of signals, right? So we started continuous time signal and we had discussed many things, right? In fact, we have started last time in the last session we have covered the frequently encountered signal, which are also known as you can say standard form of signal, right? Some standard signal which we use in control system and other applications, right? So in this session, what I'm supposed to talk here is I'll talk about sync function. Last time I discussed about pulse, okay, pulse signals. I talked about rectangular pulse. Okay, so in this session, what I will be discussing is the sync function, and sync function also plays an important role. Okay, in digital communication and everywhere. Okay, you will find sync function has got many applications everywhere, right? So remember this. So this is going to be lecture number 4. Okay, and in this session, I will talk about sync function and other concepts like how to differentiate any discontinuous function. Okay, what are the challenges we are going to face with respect to mathematics. Okay, so we have to consider those challenges also in signal and system, right? So if any discontinuous function is going to be, still we will differentiate, but we have to see how can we differentiate any arbitrary signal, right? Okay, so those things we have to focus here. So in this session, what I will talk is the sync function. The sync function, you can say the sync function. Okay, many students have a lot of confusion related to this function sync. Okay, so in this session, I have all the concept will be clear, right? So I hope my voice and everything is okay. And yes, let me check also so that I can verify it, right? Yeah, fine. So yeah, everything is clear. Now let's move ahead. So what is this sync function basically? How does sync function look like? Okay, so sync function will be encountered in many contexts, okay, and it is defined as, okay, it is defined as sync of t. Okay, sync of t is equal to sine pi t by pi t. Okay, sine pi t by pi t. You can see here there are two functions. One is sinusoidal and one is 1 upon t. Right? So you can also think this function as sine pi t, okay, into 1 by pi t. If you forget about this pi, it is nothing but product of two you can say function, right? So sync of t is defined as what? You will find this sync function everywhere in digital communication, in communication system most of the time, and in signal system also. So the sync function sync of t is defined as what? Sine pi t by pi t. Okay, so there is a sinusoidal and there is 1 by t, right? So you know that how does sinusoidal look like? Okay, it will be having many oscillations. Okay, and sine pi t is also periodic signal, right? And 1 by t is the odd function. Okay, and it is just like a kind of, you will find that this kind of a 1 by t is nothing but this, you can see 1 by t. Okay, 1 by t is going to be like this. Okay, so please remember this. So what we are doing here is we are multiplying these two functions. Okay, so how does sync function look like graphically? That we have to understand. Okay, so sync of t is defined as what? Sine pi t by pi t, and since sine term oscillates and while factor 1 by t decreases with time, that you have to remember. So sync of t shows decaying oscillation, right? What does sync of t will show decaying oscillation, right? So this sync of t will show decaying oscillation, right? Decaying oscillation. Why it will show decaying oscillation? Because sine pi t is sine pi t will show you oscillations, and 1 by t will show decay one, right? Okay, it is going to decrease as you increase the time. Okay, so sync of t is equal to sine pi t by pi t, that you have to remember. And if someone is going to ask you what is the value at t equal to 0, right? Suppose somebody will ask what is sync of 0. Okay, so since it is given sine pi t by pi t, so what you can do here is it will be a 0 by 0 form, you can say. If you put 0 here and in the denominator 0 as well, so it is 0 by 0 form. So you can apply the limit here. Okay, you can apply the limit and you can find the So you can say that limit t tending to 0, right? Sine pi t by pi t. Okay, sine pi t by pi t. That will give you what? You can apply the it is 0 by 0 form, right? So you can apply L'Hopital, okay, and then differentiate this, right? Numerator as well as denominator until you become free from 0 by 0, right? So it becomes cos, sine pi t has a differentiation pi cos pi t upon pi. If you put 0 now, so you will get 1. So you can understand that sinc of t at t equal to 0 is going to be 1. That is what the maximum value of sinc of t, right? That is going to be the maximum value of sinc of t, right? So sinc of t is defined as sine pi t by pi t. That you have to remember, sine pi t by pi t, okay? And always sinc of t will show you decaying oscillation, right? It will decay and then there will be a decaying oscillation, right? Because 1 by t is present and 1 by t is a decreasing function along with the time. Okay, so let's move ahead. So you can also approximate this, right? This is one way of finding sine like sinc of 0. There is another way you can say, right? Sine pi t by pi t. So you can find the value of you can apply the limit here as well, right? So you can say that it is approximated as pi t by pi t simply. You will get 1. Sine theta is equal to theta, you can say, right? So this is how you can also find the value of sinc, okay? So sinc of t at t equal to 0, sinc of t at t equal to 0 is going to be 1. It is for sure, right? Okay. Now, if I want to sketch here, right? Suppose I want to sketch. So how does my sinc function look like? Okay. How does my sinc function look like? That I'm gonna show you. So I will directly show you the picture here, right? Okay. So you can see the picture. Okay. There are two pictures basically. One is sinc function and one is sinc square function, right? You see, this is how sinc function look like. Okay. You see here this thick thin line, okay, this is going to be a sinc function, this, right? This is a sinc of t, right? Sinc of t. Now these black, you can say dark line, okay, dark line is going to be a sinc square t, right? So sinc t and sinc square t are going to be same only, right? Okay, but what is the difference here? This negative oscillation become positive one. Okay, that you have to remember always, right? So sinc of t look like this. Let me draw also for you. So the most of the energy is going to concentrated about this, okay, like you can say from -1 to 1, okay, and then it will be looking like this. See, it is a decaying oscillation, okay, understood? And if you are going to square of this sinc square t, right, sinc square t, so the sinc function is going to be look like same, but this negative oscillation will become positive one, right? So please remember this, the plot of sinc function and sinc square function, okay? Sinc function as well as sinc square function. Now let me tell you one thing here. Suppose we have got sinc of t and we want to plot here, right? Sine pi t by pi t, okay? So we need to find what is the value at t equal to 0. So we got sinc of 0 is going to be 1. Now we want to see that where this sinc function is going to be 0, right? So how can we say that sinc function, the function becomes 0, sinc of t is equal to 0. If you want to say that the sinc of t is equal to 0, means you have to make sure that the sine pi t is equal to 0, right? So when sine pi t can be 0, right? When sine pi t can be 0, when pi t is going to be what? Pi t is equal to this. When t is going to be what? When t is going to be plus minus n, right? Plus minus the integer, you can say, right? So n can be 1, n can be 2, n can be 3, n can be anything, right? So n should be integer here, remember, okay? So that is the reason we have written here this is 1 and this is -1, then my 2 -2, right? So you think of under sinc or any sinc square t, right? Let me write also that point is very important point, guys. Understood? That point is very important point. So you have to remember always. Okay. Area under any sink or sink square T. Nobody knows these things, right? Nobody knows, okay? But you have to know any sink or sink square, okay? Sink square. See, any sink means what? It can be sink 5T, sink 10T, whatever, okay? Sink 2T, sink square 2T, sink square 5T, whatever you take, right? The area under sink, any sink or sink square T is going to be equal to the area of inscribed triangle ABC. If you remember this, you will never face any problem, while finding the energy of sink function at all. You don't have to go for Fourier transform, right? Many people, what they do is, whenever sink square T is given, integration sink square T dt, they have to find energy of the sink function, right? So they simply go for Fourier transform. That is, yeah, that is very simple. You can go for that. You can use Parseval relations, right? But if you have got some easy method, right? If you have got some easy method, you can use this easy method, right? And you can easily find out the concept. So I'm here always, right? Dheeraj sir is going to give you one of the wonderful techniques, right? Which can help your solution very amazing, right? You can get any answer very quickly. Fine. So I think this is clear for all, right? Fine. So this is very important concept that you have to remember. Okay, so the sink function is square integrable, you can say, right? Okay, but not absolutely integrable. Absolutely integrable is going to be very useful when we will talk about Dirichlet conditions, or when we will talk about Fourier transforms, okay, and so on and so forth, right? So absolutely integrable is very important concept, right? So let me summarize everything, okay, about sink function. Okay, so sink function is basically what you see here. These are the points that you have to remember. Okay, the signal sink T has even symmetry. Okay, this is the first point that you have to remember. It has unit area, or you can say it has unit energy, and unit spaced zero crossing, right? Zero crossing. And you can say that sink of T look like this: sine pi T by pi T. Sink of 0 is nothing but 1. How do you find out sink of 0? By using some limit concept. Sink of T is 0 when T is going to be plus minus 1 plus minus 2. This is going to be zero crossing only, right? So you have to remember this fact. The sink function is square integrable, right? Like if somebody is going to ask you what is the square of the sink function, right? Sink square T dt, which is going to be 1 only. Okay, understood? So area under sink or area under sink square. See, area under sink square is what? That is energy of a signal, right? Energy of a signal, and energy is going to be concentrated in a main lobe, right? So you have to remember these concepts, okay? So I am pretty sure that you might not be knowing these concepts earlier. I mean, thinking about that plot, sink plot, okay? As a you just try to inscribe one triangle and try to find the area of the triangle. That is going to give you the area of the sink function. Any sink function you talk about, area of the sink square T, okay? Area of the sink square T. Fine. So suppose you know that area under sink function is what? 1. So suppose somebody is asking area under sink of 5T, right? dt. So here what you can do here is you can use the concept of scaling. If your scaling time, if your time scaling is done, right? If time scaling is done, so your area also going to be scaled by what? That alpha, right? You can say that the area will be here 1 by 5, right? So don't try to go for Fourier transform, and you can don't waste your time for 1 or 2 minutes at least, right? Because you will find the Fourier transform. Okay, many people do not know how to find Fourier transform directly. Though once I will conduct a session on Fourier transform, you will enjoy that, right? Okay, so remember area under sink square. Suppose someone is going to ask you sink square T dt, so you will say 1 only. See, area as well as the energy both are same. Okay, this is one of the very beautiful property this sink guy has, right? Sink of T and sink square T. The area under sink T and sink square T both same, right? Area under sink square T is nothing but energy of a sink function, right? And area under the sink function is nothing but, that is not the energy basically, but both are same. Okay, So as I told you that if you're going to scale, right, if you're going to do time scaling in any kind of signal, right, so that is going to affect your area or energy. That is going to affect your area of energy, right? So please remember that, okay? Many times question will be asked, okay, and you have to be ready, and you can get in 5 seconds to get the answer of this kind, right? Okay. So this is one concept, sync function, and there is one more function that is called sampling function, even SA of t, or sampling function we call it, SA of t. Sampling of t is look like sine t by t. You see here, I told you sync of t look like what? Sync of t is nothing but sine pi t by pi t, right? Your SA of t look like sine t by t, right? What is the difference here? There is no pi here, but here pi is present, right? Okay, so you can also plot, right? SA of t and sync of t look like the same, okay? Okay, but zero crossing might differ, right? Zero crossing now will be different, okay? You have to remember now zero crossing is gonna be n plus minus n pi, okay, plus minus n pi, because your SA of t is going to be 0 for t equal to what? Plus minus n pi, right? Plus minus n pi, you can say. Understood? Okay, this is very important, where n is equal to what? 1, 2 and so on. N should not be equal to 0 here, because at n equal to 0, okay, this SAW of t is going to be what? In last, also you have to remember here, right? Here t should not be equal to 0, right? At t equal to 0, sync of 0 is going to be 1, right? So use mathematics always. Right? Sync of 0 is going to be what? Sync of 0 is going to be 1, right? Fine. So these are the concepts that you have to remember, and you can also see the relation between SAW of t and sync of t, right? SAW of t and sync of t. So if you say that sync of t by pi, right? Sync of t by pi is going to be what? Sine, right? Sine pi into t by pi, right? Pi into t by pi, right? So pi gone, so which is nothing but sine t by t, right? So you can say that SA of t is going to be equal to sync of pi by t by pi, right? Okay, sync of t by pi. Simple relation, right? So you have to remember these points. Sometimes Fourier transform is written like rectangular has a Fourier transform sync, right? If you have got some pulse like rectangular pulse or a triangular pulse, so you can always find out the Fourier transform directly, just by remembering that the Fourier transform is gonna be the sync function or sync square function for triangular, right? For rectangular, it is going to be sync function. Okay, so you have to represent in terms of sync function, provided whatever the width of a pulse as well as the height of a pulse is there, right? So accordingly, you have to understand, right? So these are the property of sync function that I wanted to talk today. Now I'll talk about one of the very important function that is called impulse function, right? Now, why I'm talking impulse function? Impulse function will help you. Suppose you have got any arbitrary signal, right? Suppose you have got this kind of a signal. This is u of t, you can say, and you want to differentiate this guy, right? If you want to differentiate this, so you can see here, this is going to be a piecewise linear u of t, right? Piecewise signal, okay? Like for t less than 0, it is 0. For t greater than 0, it is going to be 1, right? But at t equal to 0, it is discontinuous at this point, right? Or you can say that this signal is having a jump at t equal to 0. Whenever there is a jump, you can say, whenever there is a jump at certain instant of time, so at that moment impulse is going to help you, right? So impulse is one of the very important concepts. So I will tell you how to get impulse, right? Though impulse cannot be generated in the lab, okay, that is very important to keep in mind. The impulse function is basically defined based on the area concept, right? Always remember, okay, it cannot be generated in the lab. At t equal to 0, we can't generate infinite force, right? But impulse function is very, very important, right? Suppose you have got one capacitor here, and this capacitor has charge up to 2 volt, right? And suppose there is a switch here and one more capacitor you connect here, right? Suppose you want to charge this capacitor immediately, right? This capacitor is already charged, to 2 volt, okay, and the moment you put the switch here at t equal to 0, right, what will happen, your second capacitor will start charging, right? So if you want this capacitor to charge immediately, right, okay, because the moment switch is closed, this capacitor has to charge, because in parallel the voltage should be same, right? In parallel the voltage is gonna be same, understand? So what will happen here is that what will happen, there has to be a current, okay, that is going to be a delta of t current, right? Impulse current has to flow. If impulse current is flowing here, then only this capacitor can charge quickly, immediately. Otherwise, capacitor does not allow instant change in the voltage across the capacitor, right? If suppose voltage across the capacitor is 0 initially, it does not allow sudden change, or you can say it does not allow abrupt change, right? So these are the concepts we are going to be considering using this impulse function. The impulse function is nothing but what? At t equals 0, you are going to generate infinite force, which is which is not possible. But ideally, just we are talking, okay, because of we can model, okay, this kind of a thing, right, in mathematics, right? So it's fine. So you have to remember that impulse is nothing but what? Kind of a tall or narrow spike with finite area. So impulse function is defined, okay, based on area concept, based on area concept. So you can say that the first definition of impulse function is going to be what? Integration under minus infinity to infinity delta of t dt is going to be 1. This is the first definition that you have to remember, right? Or you can say this is going to be a first property, right? I will talk about how we can get this delta of t. How can we realize here, okay, mathematically? So minus infinity to infinity delta of t dt, right? And the second definition, you can say that delta of t is defined as like this, okay? At t equal to 0, it will be infinity. Sometimes in some books, some local author book, you will find that people have written 1 also here. I have seen in many books, right? But that is wrong. At t equal to 0, basically the height is going to be infinite, okay? I mean, the force is going to be very high. Okay? So at t equal to 0, you can say infinite force, and at other than t equal to 0, that the function is going to be 0, right? So your function, you can say that your impulse function is defined at t equal to 0 only, right? Okay, suppose you have got continuous time signal. See, impulse function has got many applications, right? Suppose you have got continuous time signal, right, and you want to sample it, right? You want to sample it. So what you will do, you want so what you will do, you will just multiply that impulse with the continuous time signal, right? So what it does is like, then it will give you a weighted, or you can say sampled version of continuous time signal, right? So you have to look at the signal at impulse instant, right? Suppose impulse is standing at t equal to 0, so you have to look the value, okay, look the value of x of t at t equal to 0, right? So this is how you can sample, right? So for sampling purpose, we use impulse function. So there are many applications that you can come across in communication system as well as, everywhere, right? So this is one of the very important things. So these two definitions, remember, okay? Make sure that t equal to 0, you don't have to write 1 here. That is wrong, right? The impulse function is basically what? And if somebody is asking what is the energy of impulse function, it has infinite energy, right? Okay, so don't talk about energy, right? Don't talk about energy. The energy of a signal is what? If signal has finite energy, then only you will say that energy is like that is the energy signal, right? Yeah. So you remember the impulse is a tall, narrow spike with finite area and the infinite energy, right? So this is the first definition that we have got. Delta tau d tau, area under this is going to be 1 always. Okay, and delta of t is defined like this. For t other than 0, it is gonna be 0. Okay, understood? So this is very important to keep in mind. So how does this function look like? Let me draw here. So you have to represent this, this arrow shows that here this is going, infinite, and this one shows this is nothing but an area. Okay, so you can say this is 0. Okay, this is 0 minus and 0 plus. Your signal is 0 at 0 minus it is going to be 0, 0 plus it is going to be 0, right? So this is nothing but a delta of t impulse. How do we get this? That we have to see. Okay, so any signal you take and apply the limit, okay, we'll see that we are going to realize this impulse function very shortly, right? So I think this is clear. So sinc function is one of the very important concept that is going to be very useful in signal and system when we talk about Fourier transform of a rectangular function or a Fourier transform of a triangular function, right? And it will be also useful in digital communication because most of the stream of bits, right, okay, are going to be encoded using some line coding and all. So there will be a pulse we are going to use, and the Fourier transform of pulse is going to be the input, that sinc function, right? So please remember, आप लोगों को क्या होता है ना, just you see the question and you start solving the question. You don't know about that, why we are talking about pulse, why in digital communication or any subject you take, right? I have seen whenever I solve doubt, I always get to see people do not have the concept, just they want to know the solution of that question. किसका solution क्या होगा, right? अरे यार आप solution जान के क्या करोगे बताओ, एग्जाम में तो आपसे बनेगा नहीं, right? क्योंकि रट के जाने वाले हो, right? So you have to remember these points, right? So I think this is clear and fine. So this is very important concept to remember. So an impulse is a tall narrow spike with finite area and the finite energy, right? Okay. So this is the definition that you have to remember, right? Now we will talk about impulses as a limiting representation, right? So let us see how we can get the impulse. Impulse as limiting representation. Okay. So what you can do here is just take any rectangular pulse, right? Let us take any rectangular pulse, okay? So any, you can say this is going to be a concept of generalized one, right? Concept of generalized concept, okay? So suppose let me take one rectangular pulse of width tau, you can say, and the height 1 by tau. Why 1 by tau? See, this is going to be a situation. You see, this arrow you have to follow. We have considered this rectangular pulse, right, of a width tau, you can say width tau, and height is 1 by 2. Why we have taken 1 by 2 height? So that the area can be, you know, area can be 1, right? So area under this rectangular pulse is 1, right? Now what we are going to do here is we are going to you know, you can say that this is going to be a genesis of impulse function. You see, now we are going to, you know, make this width small and small, right? So the moment you will make the width small and small, you can say apply the limit here, right? We are applying the limit, okay? So your area has to be constant, right? Area has to be 1. So what you will do, you will scale up the height as well, right? According, so if you are decreasing the width, you have to scale the height, okay? So as long as you are decreasing the width, you see here, in this case the width is like this and the 1 by tau, here again width is this. Now if you make the width small, right, I mean you can say 0, right? So what you can say here is that it is very important concept, limit tau tending to 0, right? Limit tau tending to 0, you can say that this is a pulse 1 upon tau, right? What it will give you, this is going to give you delta of t, okay? This is going to give you delta of t. How? You can say this is going to be nothing but infinity, okay? As width decreases, your impulse is going to become, you know, infinite, right? So this is how we realize the impulse, okay? I hope this makes sense to all. So this is one of the very important concepts, please remember this, right? So as we decrease the width, okay, you can say as we decrease tau, its width shrinks and the height increases proportionally, right? Okay, proportionally the width is going to be decreasing, the height is going to be increasing to maintain unit area, right? So as tau tending to 0, we will get what? Tall narrow spike with unit area that satisfies all the criteria associated with an impulse, okay? So I hope this makes sense to all, right? You can also take one you can also take other signals, like you can take what you can say, triangular pulse, okay? And you can again just make the width small and small, so height is gonna be infinite, right? So this is very important concept. So area of impulse, right? Suppose someone is asking, suppose you have got a signal x of t is going to be a delta t. X of t is nothing but what? A delta t. What is the strength here? Strength is nothing but this A is nothing but area. Remember, this A is nothing but area. So here area is this, right? Okay, but the height is going to be infinite only. Remember, okay, height is going to be infinite in case of continuous time signal. In case of continuous time signal. So these are the important concepts that you have to remember. And suppose you're going to shift your impulse. Okay, you shift anywhere, your area is going to be same. Area will not change, right? Area is going to be same always, right? So okay, so suppose signal is signal delta t minus t0. Okay, what does signal delta t minus t0 describes? Suppose t minus t0 means what? Your signal has got shifted here, you can say, but your area is going to be 1 only, right? Okay, so if you're trying to find the area, okay, so area is gonna be 1. That is very important because shifting does not affect area, right? Shifting does not affect area. So these points you have to remember always, right? So I think this is clear. Okay, so these are the points that you have to always remember. So one of the very important condition that you have to remember is this. Suppose that shift should lie between where you see this. When area will be equal to 1, that is also very important to keep in mind. Suppose these are the lower limit, this is the upper limit, right? And delta t minus t naught is there. Suppose this is going to be your t naught impulse. Okay, now this is going to be your t1, this is going to be t2. Okay, so if this t naught lies between t1 and t2, then only this area will be 1. Okay, that is also very important to keep in mind. Suppose your t naught is here. Okay, your t naught is here, right? Your impulse is standing at t naught here, but the limit of integration is tau 1 and tau 2 here, you can say, right? Then area is gonna be 0, right? Area will be 0 in this case. Why area is gonna be 0? Because this limit of integration is not enclosing this impulse, right? Not enclosing this impulse. This is also very important to keep in mind. Okay, so these are the concepts that you have to always remember, right? And one more thing that I want to talk about here is what you have to remember is what is the relation between impulse and the step function. Suppose you have got, okay, that is very important to keep in mind. So I'm just going to take okay, the impulse function is nothing but you can say the derivative of step function, right? Okay, impulse function is nothing but the derivative of this. Okay, you see, impulse function is the derivative of step function. Okay, so delta of t is going to be what? Dut by dt, ut equal to minus infinity to t delta of t dt, right? So this is one of the important relation that you have to remember, right? So because in future you will see that if I'm going to differentiate any signal, right, and there are many jumps, right? Jumps means there is a discontinuity, right? Okay, so how we are going to differentiate, that we have to remember, right? Okay, so let us see the derivative of any function, right? Derivative of signals, okay, with jumps and with jumps. So remember always, suppose your x of t is nothing but ut. Okay, suppose your x of t is nothing but ut and you want to differentiate this ut. So if you differentiate this ut, what you will get? You will get impulse function according to the relation between impulse and the impulse and the unit step. So remember this, suppose this is u of t, right? And this u of t is nothing but piecewise continuous or piecewise, you can say. So here at t equal to 0, this is what? Discontinuous, right? So remember how we differentiate it, right? So remember at jump always, okay, this is very important point. You can differentiate this x of t or u of t normally, right? For this, for t greater than 0, you can differentiate normally. Why? Because this is constant and differentiation of constant is what? Differentiation of constant is going to be what? 0. Okay, this is normal differentiation that we do always, right? Differentiation of constant is gonna be 0. That is normal differentiation that you can do. But suppose there is a jump. Okay, whenever there will be a jump, suppose this kind of a jump is there, you're coming like this and you're going suddenly up, right? It was 0, now it become 1, right? So dy by dt of a jump is going to be what? Delta function. Remember, this is very important concept that I'm telling you, right? So wherever in signal and system it is allowed, right? In signal and system, but not in mathematics, okay? If any function is discontinuous, you can't differentiate, right? But you know the constant part, since as long as this is piecewise continuous, or you can say piecewise linear, right? So you can differentiate piecewise, right? So at t equal to 0, you can differentiate. So at t equal to 0, there is a jump, right? And what is going to be the strength of this jump? Okay, strength of this jump is going to be what? This. Okay, please remember these points are very, very important to keep in mind, right? So since a signal with sudden jump may be described by a step function, as I told you, right? So derivative of such function must give what? Give rise to impulses, right? So if you take, suppose you have got this kind of a situation, let me write. These 2 points you have to remember always, these 2 points. Okay, dy by dt constant is going to be 0. You take any pulse you take, rectangular pulse, and differentiate it, right? Okay, you will get it. Okay, okay. So if you take any rectangular pulse, there will be 2 jumps, right? Okay, at t equal to minus t by 2, you can say, or at t equal to plus t by 2. So there will be 2 jumps, right? Fine. So you can say that suppose you have got xt equal to aut minus but minus alpha. Now it is shifted version of that, right? Okay, it is shifted version of that. Okay, understood? aut minus but minus alpha. So if you differentiate this, what is the differentiation? You can say this is nothing but delta t minus b delta t minus alpha, right? This is called differentiation, right? Okay, and suppose you have a graph. So graphically also you can differentiate always, right? So in general you have to remember what? In general what you have to remember always is, in general, the derivative at jump, what? Derivative at jump results in an impulse. Okay, if there is a jump, you can say there will be an impulse whose strength equal to jump, right? Okay, so strength of a derivative, strength of what? Strength of impulse is gonna be the jump only, right? How much jump you are going to do, right? From 0 to 1, matlab 1 jump you are going, you're jumping to 1, right? Suppose you're jumping to minus 1, right? So there will be a negative impulse, right? Okay, I can show you like this. So for its piecewise continuous portion, you can say we find the ordinary derivatives, that is x dash you can say x dash t. Okay, and at each jump location xt, we can include what? Impulses whose strength equal to the jump, right? So suppose I take one rectangular pulse like this, minus t by 2 and t by 2. Why we are learning derivative of signal with jump? Because in future, okay, in future we are going to learn various properties of Fourier transform, right? So we can easily find out the Fourier transform of any signal using some properties. Okay, and in that property there will be a concept of differentiation also. Some differentiation property will also be there, right? So suppose you want to differentiate this, right? So what is the differentiation of this? This is x of t, you can say. Now x dash t, what is that? It is, see, at this point there is a jump, you can say there will be a positive, no, this is a, so you can say this is going to be a only, right? Now at this point it is coming down, right? It is coming down, so there will be a negative minus a. So how much jump you are doing, right? So here you're coming down, you can say from a to 0 you are jumping. Here you are jumping from 0 to a. So 0 to a means positive jump, a to 0 is a negative jump, right? So you have to draw like this. If there are 2 impulses associated with this guy, okay, so I think this is clear, right? So this is how we can differentiate derivative of signal. Okay, so for piecewise continuous portion, remember, for constant part you can differentiate ordinarily in the way you differentiate, right? Simply normally the way you differentiate. But at jump, you have to be little careful, right? You have to be little careful. That is very important to keep in mind. Okay? So just what are the things that you have to remember related to derivative of impulse? Yeah. So 2 points you have to always remember. These 2 points you remember this. Okay, many students, they do not understand these points. Okay, that's why I'm encouraging people to watch these videos and learn from the expert, right? The derivative of signal with jumps include what? The impulses at a jump location. Okay, and the strength of impulse is gonna be the jump. How much jump? Whether it is a positive jump or a negative jump, right? Okay, so to find the derivative, what you have to do is sketch the signal and check for any jump. Okay, if you want to find the derivative, at each jump include the impulse of a strength equal to the jump in an ordinary derivative. Suppose you have got this kind of a situation. Let me draw here. Suppose this is a pulse. Okay, it is A, and you can say this is going to be minus A, right? And you have to differentiate this. Okay, now there are how many jumps are there? One jump is here, and there is second jump, okay, and there is third jump. 3 jumps are there, means there will be 3 impulses. You see, blindly you can draw now, because now your concept is clear, right? Now your concept is clear, you can draw blindly. Okay, what is the blind approach here, guys? There will be one jump here. Okay, it is jumping from 0 to A, positive jump. Okay, so I'm just going to draw here. I'm just going to draw x dash t, the derivative of this. One jump is at t equal to 0, you can say here, right? This is A. Now you're jumping from A to minus A. A to minus A. How can you get from A to minus A? You have to introduce what? 2A, right? Okay, so this will be A and minus. You are coming down here, right? You're coming down. So there will be a negative strength here, right? Okay, so you can say at this point there will be minus 2A. Right? And here you're going up. So from minus A to 0 means you have to introduce positive jump. Right? That is A. So I think this is clear now. Okay, so anybody can differentiate any signal. So derivative of signal with jump includes impulse at jump locations, right? So there are jumps, okay, and here is the positive jump. You can say if you're coming down here from here, right, you can follow the arrow, right? Just follow the arrow like this. You are coming like this at 0. Now again you are going to A, right? Suddenly you are jumping. Okay, so this is one of the powerful tool that you can use, okay, and you can simply differentiate, right? Okay, now we'll meet in the next session, guys, and there are many concepts we have to discuss. We have to talk about properties of impulse and so on and so forth, right? And I will introduce how to differentiate impulse function, that we call it we call it doublet. Okay, doublet. If you're going to differentiate impulse function, so that will give you the concept of doublet, right? And we will also see different properties of impulse, and then we will wind up the chapter. Okay, we'll start discrete time, signal, and system. Okay, and then we'll talk about continuous time signal system as well, right? So basics I will cover properly, and rest of the chapters are very simple then, right? Okay, thank you. We'll meet in the next session.